Have you ever wondered why the universe behaves the way it does? From the dawn of time, humans have been captivated by the cosmos, persistently probing its vast mysteries. We've strived to comprehend the celestial laws that govern our existence, and one theory has been instrumental in this quest: the general theory of relativity. A key that unlocks many of the universe's enigmas. It's a cornerstone of our understanding. Let's dive deep into this fascinating theory, shall we? The general theory of relativity, proposed by Albert Einstein in 1915, revolutionized our understanding of space, time, and gravity. This groundbreaking theory reshaped the way we perceive the universe and its fundamental laws. Here's a quick rundown of what this revolutionary idea entails. Rather than viewing gravity as a force, as Isaac Newton did, Einstein saw it as a curvature of space-time that's caused by mass and energy. This was a significant shift from the traditional understanding of gravity. Newton's laws of universal gravitation, although incredibly successful, were essentially about invisible forces acting at a distance. Einstein, however, proposed a completely different picture. He suggested that mass and energy distort the fabric of space and time around them, much like a heavy ball warping a rubber sheet. Other objects then move along the curved paths determined by this distorted space-time. In essence, gravity isn't a force pulling objects towards each other, but rather the warping of space and time by mass and energy. Einstein's theory of relativity was a radical departure from the norm, challenging long-held beliefs and ushering in a new era of understanding. It was a bold idea, an idea that changed our perception of the universe and its workings. In simple terms, imagine the universe like a rubber sheet. When an object with mass, like a planet, is placed on this sheet, it causes a dip or a curvature. This is what we experience as gravity. But how do we know this theory is accurate, you might ask? Well, the general theory of relativity has been tested time and again, with evidence mounting in its favor. Let's start with an oddity in our own solar system. The planet Mercury, closest to the Sun, has an orbit that's not quite as predictable as those of its celestial siblings. Over time, the point at which Mercury is at its closest to the Sun shifts slightly each orbit, a phenomenon known as precession. Classical physics couldn't quite account for the degree of this precession. Enter the general theory of relativity, which perfectly explained this tiny but significant discrepancy. Then there's the bending of light by gravity, or gravitational lensing. It was first observed during a solar eclipse in 1919. During the eclipse, stars appeared slightly out of position because their light was bent by the sun's gravity on its way to Earth. This was a direct confirmation of Einstein's theory that gravity can distort space and, consequently, the path of light. Finally, there's the slowing down of time near massive objects, or time dilation. This has been confirmed by precision experiments, such as those involving atomic clocks flown in airplanes. The clocks in flight, further from the Earth's gravity, run faster than those on the ground. These phenomena can only be accurately explained using the general theory of relativity, giving it a solid ground in the realm of physics. So, what does this all mean for us in our daily lives, you may wonder? Well, the impact of general relativity is far-reaching and surprisingly practical. It influences technology that we use every day, often without even realizing it. Let's take the example of global positioning systems, or GPS. These handy devices that help us navigate our way through cities and across countries rely heavily on the principles of general relativity. The satellites that power GPS systems are moving rapidly in relation to the Earth, and time for them passes just a tiny bit slower than it does for us on the ground. This is a direct result of time dilation, a phenomenon predicted by Einstein's theory. For GPS systems to provide accurate location data, they need to account for this discrepancy. They correct for the slower ticking clocks on satellites compared to those on Earth, ensuring that the time signals they send out align with the time on our devices. If they didn't, our GPS systems would be off by miles, making them practically useless. So even though the concepts of general relativity might seem complex and abstract, they have real-world implications that are fundamentally woven into our modern lives. It's a powerful testament to the far-reaching impact of scientific theories and the importance of understanding our universe. So the next time you use your GPS to find your way, remember that you're actually using a piece of technology that relies on Einstein's general theory of relativity. The universe isn't just vast and mysterious, it's also incredibly fascinating.